So this is lecture 8 that starts partial differential equations, and in particular Laplace's equation. It certainly won't finish partial differential equations. That's a giant part of mathematics, and we have a lot to say, and it comes up in all sorts of applications. But before I start on letting any partial derivatives appear, can I come back to a central point of lecture 7 that I didn't get a chance to treat properly? And that was, we only treated by analogy, looking at matrices, but we ought to think even more directly. In what way is the transpose of the derivative minus the derivative? And what do we mean by transpose? Well, actually, it's a quite improper notation. I've never seen it in any proper math journal. Transpose of some operator. Certainly the idea is central. Often some other symbol. It's the dual operator or the adjoint. Adjoint would be the most frequently used word. Maybe a star is pretty common. But let's stay with transpose, because why use a new symbol when really we're speaking about the same idea? Okay. Now, so to get a little deeper here, we have to remember what the transpose was about for matrices. I mean, with matrices, we just flipped it across the diagonal. But why did we do that? And the real reason is in this formula. If I have a matrix A and a vector U and a vector W, I can, and they're the right sizes, I can form A times U. I'm always thinking of A as m by n, and then U has n components, and then AU has m components, and so does W, so I can take the dot product. Okay. Now, the point about matrices, which we can just check by expanding out all the little terms that show up there, is that I can, that expression is really, if I write it out, it's U transpose A transpose W. And the point about these matrix operations is that I can put the parentheses in there if I want to. And I do, because now I see what A transpose really is. A transpose, the reason we flipped it across the diagonal was to make this formula right. The correct, if this is a dot product, two vectors, then this formula becomes correct if A transpose is what we understand it to be. Why do I make that point? Simply that now if we take the idea of inner product, dot product, over to functions, and we ask for this rule to still hold, it will tell us what the transpose should be for functions. So so this is a dot product of E with W. So just let's a little time out here. E transpose W. Those are vectors, so it's a sum of E I, W I from I equals 1 to m, right? That's what the dot product is. That's what this operation was. Now, suppose these are functions. Suppose E is a function, as it was, and U is a function, as W is a function, as it was. And by the way, this dot product is quite physically significant. This E transpose W, that's what, strain times stress? That's internal work. I mean, so these dot products are not like accident. Nothing ever happens in mathematics by accident, so to speak, I think. And this expression has a physical meaning. but what I want to know is how should I change that definition when I'm dealing with functions? Okay. So what do I do in the function case? Well, instead of summing, what do? I integrate. Right. So that's the dot product. I integrate over whatever region the functions are defined, and in that lecture, x went from 0 to 1. That would be the dot product somehow. This is E transpose W for functions. And it's just perfect. When would these vectors be perpendicular to each other? When would we be doing no work? E transpose W, when E transpose W is 0. Our geometry, our picture of, in case E transpose W is 0, the picture in our mind is two perpendicular vectors. Well, now you got to think of two perpendicular functions. And what the heck? Well, that picture is getting blurry, right? But what does it mean for one function like sine x to be orthogonal to another function, maybe cosine x? It would mean that the integral, the dot product, is 0. What I'm saying is all the sensible things that we can visualize in 2 dimensions, almost in 3, we can pretend we understand in 4 and 5 dimensions, is fine here in infinite dimensions with functions. Okay. Now, so that's the dot product, and that's why I did this integral. This is the integral from x equals 0 to 1. Okay. Now, I want to get, I'm copying this, do you see? I want to get U by itself and throw stuff on W. And this is got to be like just an identity. That's the way this was an identity. But this identity is going to identify what A transpose should be. Now, how do I would like to have, as I said, I'd like to have U by itself, and whatever should move on to W. So what do I do here? I integrate by parts. Integrate by parts. Now, I don't know if you ever paid any attention to integration by parts. Because one of the troubles is it's only introduced in calculus as like a way to integrate certain otherwise unpleasant functions. Like maybe log x or something you can figure out its integral by using this silly trick. But my point here is really that integration by parts is far from just a little trick and is much more fundamental. One of the most fundamental things I could put in any lecture is integration by parts. And what's the rule? You remember that the integral, still from 0 to 1, I take the derivative off of U, and I put it onto W, but what's the key point then? In integration by parts, there's a minus sign. So let me put it in here. So that's integration by parts, almost perfect, but now, and it's enough to make the point that A transpose W is there. You see that integration by parts has produced the minus dw dx that so integration by parts is the way to transpose derivatives. But always boundary conditions are an issue, and of course this formula isn't exactly correct, is it? There's a boundary term, and what's that boundary term? It's U times W evaluated at x equal 1, the upper limit, minus the value at the lower limit. So now I've got the integration by parts formula completed. And somehow I want this to be correct, even with this term in there. And the boundary conditions have got to deal with that term, right? In the inside of the interval, it's minus dw dx, but we know that at the ends of the interval, that's where the boundary conditions come in, and But think of the boundary conditions that we had. We had two examples. In the fixed case, u was 0 at both ends. So what happens to this? It vanishes. It's gone. What about the fixed free case? U was 0 at one end, W was 0 at the other end. So what happens to this thing? W vanished, again, gone. So in a way, the boundary condition on W, and maybe I just say this here. If we start with the operation A, which is on U, and has any boundary conditions that apply to U, then we integrate by parts, and we find out what A transpose is, and we also find out what the boundary conditions are that go with A transpose. The operator and its adjoint are like, you know, they're together. If I know the operator A, then that tells me what its adjoint has to be, just the way I know the transpose of a matrix. Okay, this is discussed also in this section of the book, and this a little thinking here. But at least I could make the point, first, the crucial nature of integration by parts, and we're going to see the same thing now for partial derivatives. So I'll move to partial derivatives, and remember, we're going to have to transpose somebody, and the way we'll have to do it is an integration by parts, but we'll be in a plane. It'll be an x and y derivative, not just x. Okay, so let me go to that point. Okay, so now I'm in a plane region instead of an interval, and of course the shape of the region is going to be highly important in whether we're able to get anywhere with pencil and paper, or whether it's going to be finite differences. For a circular region, we can get somewhere with pencil and paper. But anyway, we've got a region there in the xy plane. So this is a region R, let's say, in the xy plane. Okay. Okay. And what's the... Well, let me jump right into the framework, as I often do. So I have a function u of x and y. Okay. That could represent a potential. If we were speaking about ideal fluid flow, I don't know what example you will prefer. The potential it might be. A potential function, or a temperature. Could be a temperature if we were discussing heat flow. So it's the let me use the word temperature. Okay. Now we need, as always, an A, which will take us to a, I'll still call it E, maybe. E will be AU. Okay. What's going to be the natural example here? Over here, A was derivative. First derivative. That's the natural starting point. So A is going to be first derivative here too. But we've got two derivatives, two first derivatives, the x and the y. So A is going to be, A better tell us both of them. A will be d by dx and d by dy. So that AU is now du dx and du dy. We've got two functions. So this guy, this thing is now a vector. This was a scalar. We have to pay attention to what's up here. This was a scalar function. Now we've got a vector because we've got two components. And what's the name for that? It's just like a vector that contains the two first derivatives. And then, of course, so we're into multivariable last semester calculus here. And but I hope, actually, that some of that last semester calculus will become clearer by using it. Okay, so what's the name for this thing? It's the gradient. This is called the gradient of u, and grad for short. And there's some sort of a triangular symbol, but I feel more comfortable writing the 4 letters grad. So A is the gradient operator. And then we apply it to u. Okay, and then as always, off comes some kind of conductivity if it's a heat problem. So this is this is like temperature differential, right? This is, if we were in the discrete case, it would be. Here, yeah, it's sort of, you know, a temperature gradient. You know, how steep is the temperature gradient? That tells us how quickly heat's going to flow, right? Right? I mean, always, there's somebody's law here, and it says that some differential produces some flow. And this would be, C will be some conductance or conductivity or something. And it could vary from point to point, but if we're going to do anything with pencil and paper, we'll hope that it's not varying, but it could vary. Okay, so we get a W of x and y, which is again a vector, which will be, in general, some C of x and y times grad u. So remember, that's a vector. So I'll just momentarily at least put a little arrow on these two guys to remember that those are vectors. Okay. And now, of course, the moment comes when so this is the flow of heat. And so now we're going to have an equation of balance. There may be some heat coming externally. We may be, you know, holding a candle under part of this region, or putting ice there, or something, doing something externally, or it may just balance to 0. That will be the case that we'll study the most. So there'll be an A transpose here. And would you want to guess what A transpose is? Well, if A is this, let's just work by analogy, and then, of course, it's going to be some kind of integration by parts that'll look like be more legitimate. But what do you figure for A transpose? So A was like this 2 by 1 operator. I think A transpose is going to be 1 by 2 in a way. And what's the transpose of d by dx? Negative d by dx. And what's the transpose of d by dy? Negative d by dy. So those are the two. You could say this is a block operator, 2 by 1. This is transposed as a 1 by 2 block. Okay, so now what's our equation? Our equation is going to be A transpose W equals this right side, as always. So that will be minus, okay, oh, now are we in good shape here? Let's see. This is supposed to act onto that. What's happening? It's going to work. So, right, I'm multiplying a 1 by 2, and this guy's 2 by 1. You're okay with that? So it'll be minus d by dx, this guy, applied to c d by dx, good, the first component, minus, now I'm ready for this guy, minus this guy times the c second component of the gradient equals f of x and y. These equations take more space now. Okay, I've written it out to see that it really is a partial differential equation. And a highly important one, the most important steady state elliptic partial differential equation. Well, the most important special one is if C is 1 and F is 0, then we, of course, it should simplify. If C is 1, I can ignore C. If F is 0, I have 0 on the right. So I have just minus the second derivative of u with respect to x minus the second derivative of u with respect to y equals 0. And that's a famous equation named after Laplace. That's like the, that's named after Laplace, and if we're going to solve any partial differential equation, that's the one we better tackle. First, because of its importance, and then also because it's relative simplicity. Of course, it's still a PDE. You can never, it never pays to underestimate a partial differential equation. Okay, and finally, just so we get the, this is minus, anybody recognize? So this we had we knew a name for it. It was the gradient, d by dx, d by dy. Now there's also a name, inevitably, because it's so important. The transpose of the gradient is minus. So do you see what the, you know, if I apply A to, everybody's seeing how I'm applying A to W. If I apply A transpose to W, this is, W has two components. And what have I done? I've taken minus d by dx of the first component, minus d by dy of the second component. And what's that called? There's a divergence. That's a divergence. I'm taking the divergence of the vector W and with a minus. So this is minus the divergence of W. So in other words, we're discovering that I frankly was happy to realize that the transpose of the gradient was minus the divergence. That's maybe, you know, of the pleasant things to say in this lecture, that's certainly one of them. That the transpose of the gradient is minus the divergence. So far, totally formally. Totally formally. But maybe we should take a second to make it, I mean, when I said formally, I meant informally. I meant just like it seemed right. Now let's maybe take another second, since we discussed it in 1D, to make it seem even more true. Okay, but this is like maybe will be in these lectures like maybe the climax of the framework to make Laplace's equation pop out here for partial differential equations. And again, I'm hoping that you pick some physical problem like temperature gradient, flow of heat, balance of heat as a model, or if you like fluids. So how would we think of fluids? This U, if it's some potential and it's a fluid flowing around the plane in steady state. Again, steady state. So it's got a, then this would be its velocity. If this is the potential for fluids, this thing might be the velocity of the fluid. And it's not changing with time. We were talking about ideal, very ideal flow here. You know, we're not near the Navier-Stokes equations. So this would be the velocity, and this, what would W be? I'd be multiplying probably by maybe the density. So maybe W would represent momentum. I'm multiplying a sort of a mass by a velocity. Might be a momentum term. I don't know if you like fluids. I'm far from being an expert, but I just felt I should give an alternative set of words that would describe our problem. And then this balance would be a balance of to be in steady state, at around every point or in every region, the flow in has to equal the flow out. This is, in some form, it's Kirchhoff's law. In some form, we have a network here, but it's a continuum. For me, that's quite instructive, to think of our original networks with Kirchhoff's laws and that fundamental Kirchhoff current law, charge in equals charge out, flow in equals flow out. That's what we have here. But now flow in and flow out would be applied to any little square or any little region, or the whole thing. Flow in has to equal flow out because we're in a steady state. Okay, now I guess I better, since I'm so close to, having put this discussion up, why don't I put up the corresponding integration by parts, and there will be a boundary term for 2D. So what's this? What do you figure is going to be our identity? Green's formula. It'll be Green's formula, which is just integration by parts in 2D. So, all these important formulas are just like they grew out of something simpler. So something simpler here was integration by parts. Even simpler was summation by parts. Now we're going to have double integrals. AU is going to be the gradient of u, which is a vector, times w, which is a vector, and integrated dx dy. And let me put a temporary little reminder. So that's actually a dot product of two, because this has two components and that has two components. So I have a du dx times w1, and I have a du dy times w2 in this, right? This is that right? In this thing, I'm seeing a du dx multiplying w1, and I'm seeing a du dy multiplying w2. I'm sorry. I apologize to bring in multivariable calculus formulas. I promise to do as little of it as possible, but this is as little as possible. Okay, and this is a double integral over our region R. Fine. Okay, so what's the other side of Green's formula? What's Green's formula going to be? It'll be a double integral over R. Okay, and I'm taking things off of u and dumping them onto w. So it'll be a u times, what do I dump onto w? Dx dy. Plus boundary terms. Oh dear. Probably Green figured out what they were. So there's a plus boundary terms, and then tell me what goes in here. Okay, you might want to do it by looking at these two pieces separately. So just think. I'm taking the x derivative off of u and putting it on w1. I'm taking the y derivative off of u and putting it on w2. And then I'm putting those two pieces together. And there's a minus sign when I do that, when I do the taking off of one, putting onto the other. So what do I have in here? I have minus the first guy with respect to x, and I have a minus w2 with respect to y, and what is it? That's the divergence. Right. So what we're seeing in here is minus the divergence of w. So that would be a fundamental identity of two-variable calculus, that the integral of the gradient of u with w gives me the same as the integral of u with minus the divergence of w. Notice these are scalars. I don't put arrows on those. And then finally, there's got to be a boundary term, which we might as well get this close, get this far. Let's go for it. What would be appropriate? What form will the boundary term take? Well, the boundary is this. This boundary, B, is this curve. It's a one-dimensional curve. So this will be an integral around the boundary B of something. You see the boundary is like one dimension lower. Here this was a one-dimensional integral, so the boundary terms were points. Values at points, 0 and 1. The boundary of the interval from 0 to 1 is those 2 points, one dimension lower, from dimension 1 down to dimension 0. The boundary of this 2D region is 1D. Okay, and so what do we integrate around this boundary B? Well, that's what calculus ought to tell us. So this is an integral around the boundary. And what do you figure we've got here? Well, you figure a u, no problem there. What's not so obvious is what is the w factor? Why can't I just write uw the way I did in the boundary term in 1D? Because w is a vector and u is a scalar. And like life should stay right. And it turns out that what it is the normal component of w. So it's the integral of u, the scalar u, times the normal component of w, which may be w dot n integrated around ds is the usual letter for integrating around the boundary. Okay,
It's normal to the boundary?
Yeah, n is defined as the unit. Whoops, does that look normal? If this is going on tape, let me try to get. So that's n is the unit normal vector going out at every boundary point. So you see, right away we see, okay, it's a little not so. Well, in a way, what was the unit normal vector? I ought to be able to go back and see this in the easy case. What was the unit normal vector pointing out of the interval in this, when it was an interval? Well, what were the boundary points? There was 1. Where's the unit normal? Well, I don't know. I think it's that way. And here, the other way. So maybe that even explains the reason that had a plus sign and that had a minus sign in the boundary term. You remember the boundary term was uw between 0 and 1. At least I like that idea anyway, even if it's possibly ridiculous. It's still sort of so this is an identity then. If I take, and it's the fundamental idea, it's Green's formula. Probably Gauss knew it too. I think it's often called Gauss-Green formula. And it's integration by parts in 2D. It's taking derivatives off of u and putting them onto w and watching for the boundary term that appears. And if the region is a rectangle, we could give a justification, but I think done enough to get it up there. Okay, so you saw that happen. So what sort of boundary conditions would we expect in our problem? So I've got the framework here, but I haven't done the tricky part, the boundary conditions. So tell me what kind of boundary conditions could I impose on, say, in the temperature problem. Okay, I have a region, and I'm heating or not heating some interior parts. F could be quite possibly be 0. All the action could come at the boundary. And what could we do at the boundary? Well, we could maintain part of the boundary or all of the boundary at certain temperature. I could, so boundary, so let me go for it here. Boundary conditions. I could have u equals some specified function u0, maybe on part or all of the boundary. And what else? What's my other option? A condition on w dot n. I can't prescribe both components of w. That's two boundary conditions at a point. This is only a second order equation. I'm expecting to prescribe one boundary condition at every boundary point, just as always, just as we've done. And I could prescribe u, or I could prescribe the normal derivative. So this would be or w dot n. So this is like prescribing the temperature, like saying, okay, I'll hold this part of the boundary at freezing, at 0 degrees maybe. Okay. And on this part of the boundary, it's what would be the word? I can prescribe w dot n as whatever I like, maybe some f on the rest of the boundary. Okay. I'm hoping these and this series of lectures will not, we're not going to disappear into multivariable calculus and never reappear again. But I think Laplace's equation is so important that it's right to see it in our framework. It's right to see what the boundary conditions might be. And then it's going to be right to try to think how we might solve it. And of course, solving Laplace's equation is going to be a bigger job than that two-point ordinary differential, two-point boundary value problem with an ordinary differential equation. I'll still be interested in a delta function, a two-dimensional delta function as an important case. And I'm certainly interested also in 0 as an important case, and then let the boundary conditions provide the action. Okay. So any question or discussion while we're sort of taking the big view, recognizing that the gradient and the divergence, actually what I ought to do now is focus a little bit on those separate pieces. Can I focus for a little bit to understand the divergence? Yeah. Let's understand, what does divergence mean? Understand a transpose. Well, what do I mean by understand it? I mean, well, like, I think of this as totally analogous to Kirchhoff's current law. And for Kirchhoff's current law, we succeeded to solve the system of equations. So let's try here. So this is like, so this is minus divergence. And now can I try in this corner? So this corner is a discussion of divergence. Okay. What is this? So the divergence, so let's just be, I better write down again. The divergence of W is dw1 dx plus dw2 dy. Okay. So that's our A transpose, W. And I guess I'm interested in what, well, could we solve, so Kirchhoff's current law, if there were no source terms, would be the thing should be 0. And we would expect to be able to solve that. So could we solve, tell me some solutions to, so I'd like to solve divergence of W equals 0. And I'm certainly expecting lots of solutions. This is our, A transpose is our wide, short matrix in the discrete case. More unknowns than equations. You see, actually, I've got one equation and two unknowns. So tell me a vector W. It can depend on x and y. Of course, if W is a constant field, if W1 is a constant and W2 is a constant, then of course the divergence is 0. So that would be one example. Tell me another W. So can we just like build up a few examples?
Linear with different slopes.
If they were, okay. So what would another, so examples. So just to be sure, W, it's got two components. So tell me two functions that work. 3x here and minus 3y there. Right. Okay. Any others that? Two constants would certainly work. We got a lot of freedom here, right? I mean, if I tell you W1, you could probably tell me what W2 had to be, right? Suppose I tell you W1 is x squared. Okay, this is like fun. If W1 was x squared, then I think you could probably figure out a W2 to go with it. And what would it be? Yeah, so the dW1 would be 2x, and we want to get a 2x out of that. So, and a minus. So maybe minus 2xy? Is that it? Okay. So that would work. And plus c. That's right. We've certainly got an arbitrary constant in both of them. That's right. If we add any two, in other words, we're struggling or moving here toward. Can you tell me all? Is how could we handle all the solutions? Oh gosh. I'm looking for a function. I'm looking for two functions. The x derivative of one plus the y derivative of the other is supposed to be nothing. I don't know, how do we, I have a thought here. Can I describe my thought as a way to, because you see what I want to do now is to try to write down all the solutions. Somehow get a handle on them all. Now, here's my thought. Suppose, suppose W1 was the y derivative of something, of some function. So let me imagine there's a function s. So now I'm trying to get all solutions. Okay, if I can, all solutions to div w equals 0. This is my equation. Better be sure we know what we're doing. Okay, I'm looking for all solutions. Okay, let me start with any. Okay, take any function s of x and y. Let me call it s of x and y. S of x and y. And now, here's the key. Suppose let W1 be the y derivative of s. You'll see why this is a possible way to go. What would W2 be? What would W2 be? So what will we have in our equation here? We'll have dW1 dx, which is what? is the x derivative of the y derivative of s. It's looking a little funny, but you'll see that it's worth it. This term would be, so I take any function s. So there's going to be I'm claiming that there's some function s hiding behind this answer. And that w1 could be the y derivative of that function. And then what will I have here? Mixed derivative. I'll have the x derivative of the y derivative. Okay, now do you see what w2 should be? If w2, I want to get that mixed derivative with a minus sign. So then I'll do it with yellow. Then w2, I want to have the minus sign because I want to cancel. And what should w2 be minus what? Partial of s with respect to x. Perfect. Partial of s with respect to x. Great. That gives us a whole lot of solutions. And in fact, it gives us all of them. In fact, let me just test it on one. What's the s hiding behind here? So that this, I hope, is the y derivative of it. So what is the s here? X squared y, because the y derivative of that will be this. So the s that's hiding behind is x squared y. And now if our reasoning was right, this should be what? This should be minus, which is either minus anyway, the x derivative, and the x derivative is 2xy, right? So that's my suggestion, is that if we're focusing on the divergence and we wanted to know solutions to Kirchhoff's current law in this continuous case, that they would come from this s, and I even have a name for that s, the stream function. So somehow the stream function is a suitable name when I'm thinking of this flow problem. I don't know what to call it. Maybe it's iso something. I bet it's iso whatever. Iso bars. What's an isobar in temperature? Oh, it's some constant pressure. It hasn't got a lot to do with temperature, does it? Iso, what is it? Therm. Isotherm. Now, no, that isn't right. That isn't what because the stream function, I'm putting a lot of words up here. This stream function is not the same as the potential function. S and U are not the same, but boy, are they like twins. In some way, the lines U equal constant, what's the right word for those? Equipotentials. A line in which, a curve along which U is a constant is called an equipotential. The potentials equal all along the curve. A line on which the stream function is a constant is called a streamline. And that tells which way the fluid is going. The fluid is traveling along streamlines. If you drop a leaf in the fluid, the leaf will follow the streamline. And those will be perpendicular to the equipotentials. Oh, I'm really far ahead of myself here. But I think it's worth getting some kind of physical sense of what the problem is. It's sort of pleasant, at least, to get some physical sense. Flow is going on here. Maybe we're feeding fluid in here, and it's coming out somewhere else. Whatever. So flow is traveling, and if we drop a leaf in the flow, it'll follow a streamline. And if we drew the lines where U was constant, it would be perpendicular. So somehow that fact ought to appear out of this, and ultimately it will. That these curves U equal constant are perpendicular to the curves S equal constant. Okay, I guess I feel that we solved divergence W equals 0, but I don't know that I have a hang of what that divergence really means. What does it mean, the divergence of a vector field? So I've got this flow field. Everybody's going somewhere. And I compute its divergence. So I compute, what does that expression represent? dw1 dx plus dw2 dy. It's sort of the rate. Yeah, the rate that stuff is leaving the point. That's really what it is. The divergence is the rate at which fluid is leaving a point. Right. And the reason we're interested in 0 is that maybe if there's no source term, then that rate should be 0. Here's a way to think of it. Take a little bit of the region, like a little square. A little tiny square, even smaller than that. Okay. So practically a point. So then the divergence at that point is telling us how much, the rate at which fluid is going out of that square. It's going out this way. It's going out this way. So there's kind of a difference between W1. It's going out this way with velocity W1 at this point, and it's going out this way with velocity negative W1, but at this point. And there's a difference between those 2 points. So there's a derivative of W1 that tells us how much is going out horizontally. And then W2 is the rate of flow in the vertical direction. And there's a flow out through the top and a flow this way, which is going to be almost equal and opposite, but slightly different based on the difference inside there, which is, in the continuum case, is going to go to a derivative. So I never said these words before, but I'm sort of seeing out of this, for flow out of that little square, that it's essentially the divergence of W, the x derivative of W1, plus the y derivative of W2, probably divided by the area of the square, because, or something, yeah. So that's how I interpret divergence. Gradient is well, we have a sense of what the gradient means. And so if I give you a function u, you could tell me it's, now I'm focusing for a moment on gradient. What's the meaning of that? So what does it mean? So I have let's think about the meaning of gradient. So I'm starting with a function u of x and y. Let's think of its graph. So what's the graph of u of x and y? So now I'm turning to the meaning of gradient and applying it to a function u. Okay. So let's try to hang on to gradient. Because of course it's the divergence and the gradient that enter Laplace's equation. This thing is just exactly, this is minus the divergence of the gradient, because c is 1, of u. That's Laplace. By the way, why the minus sign? Well, you could say because it came with a transpose. And, I mean, another way to say it is, it's the minus sign that makes the thing positive definite. Right? It's the minus sign. The minus sign has to be in there to make A transpose A appear and produce the thing. So it's minus, it's this minus, with this minus sign that this Laplacian is a positive definite thing. Right? Yeah. Yeah. So in a way, I guess what I'm saying is derivative d by dx is antisymmetric. D second by dx squared, which is twice squared it, is symmetric, but negative definite. And only if I put in the minus sign there can I change that to positive definite. Because then it's A transpose A. If this is A, then this is A transpose A. Minus sign included. Okay. Yeah.
Is this the same minus sign that comes from our flow only going down the gradient? Or is that the same?
Maybe, I don't know if it is. Yeah, I don't know. It's somehow, in a way, it's the minus sign that when I kept having these matrices, and you haven't seen the last of them, with this thing, I was going to pause and ask you about that. What do you think of when you see -1 to -1 applying to some u? In other words, when you see something like minus un plus 1 plus 2 uns minus a un minus 1, what comes to mind when you see that combination? It's a sort of a, yeah? It's like a second derivative, so it's a second difference. It's a second difference. It's the difference of a difference. Of course, it came from A transpose A. But normally the second difference of something would have this opposite signs. This is minus a second difference. Just the way this was minus a derivative. So I think maybe that's where this minus sign is coming in. It's coming from A transpose because we can't help it. So this is the second difference of these. I'm taking not just like the slope, u at the new point minus u at the old, but u at the new minus u at the old minus u at the old minus u at the older. In other words, difference of differences, second difference, is producing this 1 minus 2, 1, and then I reversed all the signs because transposing made me do it. And, of course, it produced the positive 2's on the diagonal and made things positive definite. Okay, so that's, yeah. Other thoughts about signs and so on. Now, I guess if you're willing to hang on for one more minute, were we going to do something to say something about gradient? Yeah, just to get a hang of gradient. Well, I made some space and then I used it. So let me this is the absolute last corner of the board. I just wanted to get to the idea of gradient. Okay, gradient of u. Okay, so what's the idea of u? Well, let me try to graph. Here's x, here's y. If I graph u of x and y, I get some surface, right? All right, maybe I'm climbing a hill, right? So the surface, think of that surface, beautiful art there, as like a hill. Okay, and now I take a particular point in the base, xy. I look at that point on the hill. So that's going up to the point on the hill. That's u of x and y right there. That height is u of x and y. What's the gradient? What picture do I have in mind when I talk about the gradient? So the gradient, well, the gradient is a vector. Yeah, the gradient is a vector. Well, which way does it point? The steepest. Right. The gradient, so if I'm going to try to interpret this whole vector and not just its two pieces, which I would certainly want to do, the gradient is points in the steepest direction, like that. If that's it. Does that look to your eye like up the hill? Right. And the magnitude of the gradient is like how hard it is to go straight up. How hard is it to go in just to stay in a direction, say, where y is constant. So, yeah. What am I trying to do here? I'm trying to say the gradient is a vector. It not only tells us, like, how steep the hill is in the steepest direction, it tells us how steep it is in every direction. How do we find out how steep? Suppose you want to walk in another direction. Not such hard work. So climbing more slowly, suppose you take, so the derivative, the directional derivative of u, of our surface in some direction. Now, I guess I have to tell you a direction. What shall we use for, well, okay, so tell me in words. If I wanted to travel in a different direction, suppose I wanted to travel in the direction opposite to the gradient. What would the direction opposite to the steepest, then what am I doing? It's as negative as possible. And if I travel in some other direction, it's in between. And what is that in between number? I'm somehow projecting or taking an inner product or something. I'm taking the component of the gradient in the direction I'm going. Right, that's a good way to look at it. It's a dot. It'll be a dot product. It'll be it'll be the gradient, which is the steepest, dotted with the direction. What letter shall I use for direction? I hesitate to. Well, just direction. I'll write it out. Say a unit vector in the direction, a unit direction vector. Okay. So the absolute steepest, the biggest I can make this is for that direction vector to be lined up with grad u, to climb the hill as fast as I could, and then this would be a unit vector. The cosine would be 1 between them, and I would get the gradient, the magnitude, as the steepest way. The opposite direction, I would get minus. And what direction would I climb? Would I be staying level? So what's my level direction? When the dot product is 0, right? And so that would mean what? I don't go in the direction of the gradient. And what direction do I go? You said it. Just say it again. I go orthogonal to it. If I travel orthogonal to the gradient, then I'm on an equipotential. Do you see it's connecting with what I was saying before? The equipotentials will be, oh, God, what looks like equipotential on that? I don't know. Somehow, this is supposed to be not climbing, just, having a pleasant hike by staying at the same. So this is an equipotential, u equal constant. I don't know if your eye is saying that that should be that should be a right angle there. That's the steepest way. So that's the streamline. Okay, the analogy there, the streamline is the leaf is traveling in the direction of fastest change in the direction of the gradient. That's what this produces. This is a velocity. So the streamlines are those guys. So, yeah. So suppose I'm on a mountain, and I spill the water I carried up to drink or something. Okay. So how does that travel down the mountain? Or it rains. That's more realistic, right? Okay. So it rains at the top of the mountain. Then how does the water travel downwards? Down the gradient, right. So those little erosion gullies are in the direction of so that's the streamline. And perpendicular to them would be a line of equal potential. Right. Okay. Okay. So in other words, equipotential, I would cut this surface by a horizontal, and it'll cut it in an equipotential, because horizontal plane would be u equal constant. So it'll cut the surface in some curve. There'll be the equipotential curve, and at every level I get a different equipotential curve. So I really see the whole region as made up of these equipotentials. Yeah, when I come back to this topic, we'll see that in this region will be some equipotentials curves, and perpendicular to those are the streamlines. It's quite beautiful. And so these functions u of x and y that give the potential, and s of x and y that gives the stream function are somehow quite beautifully related. Okay, I think that's probably all we can do for Laplace's equation. What we didn't do was solve it, and that'll take a little while. Okay, see you next Thursday.